Okay, digging into our prerequisite chapter, right? This should all be kind of review. This is going to handle a few things: algebraic expressions, models, and real numbers. So this video is going to take you through 6 things, and these are the 6 things we are going to talk about. So first, classifying and ordering of just the numbers we know, using properties and identifying the properties of real numbers, evaluating and simplifying algebraic expressions, finding unions and intersections of sets, going back to evaluating, but now instead of just algebraic expressions, they're going to be dealing with absolute value. And last but not least, using mathematical models. All right, so this is something you're going to do in class. So over that, I'm going to jump into our notes. Okay, so this is dealing with that first learning target, being able to classify numbers. So we have all these classifications. We have something called real numbers, rational numbers, irrational, integers, whole, and natural. All right, so let's go through this. So starting off with real numbers. All right, now the way I kind of always discuss this as when we're talking about numbers, there are 2 options. All right, so I say this is kind of like a species, right? You're either human or you're not human, right? There's only 1 or 2 options. All right, we're not going to dig into different animals or anything, but you're human or not human. That's what this is the first classification of real numbers. Is it real or is it not real? Okay, and real numbers are all the numbers you've been exposed to this far. The other category, which we will get to later in this class, if it's not real, it's called imaginary. All right, this is something that'll come much later in the class, but we're not going to worry about that now. So every number we know should be real, right? And that's why I say it's any number you can think of, any number, right? The big thing about these real numbers is the fact that they can be placed on a number line. Right? You can graph these. Right? So for example, the number 2, the number negative a million, right? The number 1/2, the number 0.6423, the number pi, right? Any other weird number, the square root of 2, right? These are all real numbers. Okay, so every number you know is real. Okay, and I'm kind of going to dig into this a little bit more. Right, I say note the order I introduce these to you, and this is why I'm just going to handle that right now. Right, every number is real. Every single number we're going to run into in this class right now is real. Eventually, we'll get to those imaginaries. Right, but once it's real, it gets divided up into 1 and 2 categories. If it's real, it's either rational or irrational. So right, going back to this idea, right, you're human or you're not. You're real or you're imaginary. All right, well, once you're human, right, once you're real, you get broken down into your gender, right? Again, I'm going to use that loosely, right, this day and age, right? But, right, you're classified as male or female. All right, loosely. Again, I know there's more to that right now, but I'm trying to connect this to a way that we can see how these work. All right, so once you're real, you're either rational or irrational. You cannot be both. You're one or the other. Okay, so let's talk about that. If you're rational, that means you can be written as a fraction. A fraction. So examples of that, right? Well, easy one. 7/8, that is a fraction. 2/3, that is a fraction. Another way we could write fractions is with decimals, right? 0.25, we all know is the same thing as 1/4, right? Now we may not know how to convert this one, but isn't 0.625 isn't that a fraction? Isn't a decimal a fraction? 0.1234, isn't that a fraction, right? Isn't this technically 625 over 1,000? And isn't this technically 1, 2, 3, 4 over 10,000, right? And then you could simplify and reduce, right? Now here's the question to you, right? Would the number 4 be rational? All right, think about that. Can you write the number 4, right, to be rational? It's just saying you can write it as a fraction. Well, could the number 4 be written as a fraction? And the answer is yeah, right? You could write 4 as a fraction many different ways. The easiest way is just saying 4 over 1. That's a fraction. What about 8 over 2? Or 12 over 3? Or 16 over 4, right? Aren't these all the same thing as 4? Right, so our whole numbers, 1, 2, 3, 4, 5, 6, right, those could be written as fractions, right, any of these, right, -4, right, because you could always write these as over 1. All right, so most numbers we deal with are, well, again, right now, all numbers we deal with are real, and then most numbers we deal with fall into this rational category because most numbers are either whole or decimal. Right? Well, if you're not whole or decimal, right, that means you're irrational. Right? And what that means in math, that means it's any number that cannot be written as a fraction. Right? So what that means is those are the decimals that do not terminate, the decimals that do not end or repeat, right? Because this is an easy one, right? If I say 0.3 repeating, we all know that that is 1/3. That is a fraction. That's rational because it is repeating. Now, if you get a decimal that does not terminate, right? So 1.23894 ... etc., etc., etc. Right, that's not terminating and it's not repeating, therefore it's irrational. All right, we don't run into many cases like that because we really don't. Right, I mean, all fractions, most of the fractions, or most of the decimals we use come from fractions, meaning they will terminate. Now, the ones we do see, all right, sure, we'll run into this. The times that this happen, they happen in certain cases. They happen mainly when you have square roots or radicals, right? Because we're going to deal with cubed roots and fourth roots in this class that are not perfect, right? The square root of 2 is not a nice number. Right? The square root of 4 is 2, right? Meaning it's a nice number, meaning it's rational. The square root of 2 is not nice. Right? It's going to lead to some ugly decimal. Right? So that's a big one we see here. The other really big one that we see, and we forget that this is a number, but it is pi. Pi is 3.1415926 blah 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 blah. Right? So pi is another irrational number. Okay? So again, once it's real, it gets broken down into one of these two categories, rational or irrational. All right? If it's irrational, right? If it's irrational, we stop. All right? If it's rational, rationals then could be broken down into more distinct categories. If it's rational, it could be an integer, it could be a whole number, or it could be a natural number, right? So once you're human and once you've identified your gender, right, that what makes us different now is our eye color, our weight, our height, all that stuff, our hair color, right? That's the way we kind of think of integers, whole numbers, and natural numbers. Okay? So, I'm going to actually start from the bottom up on this one, right? So I'm going to start with the natural numbers, all right? The natural numbers are what we call, the keyword here is right here, positive, all right? That's the keyword right here, positive, and what we call counting numbers, right? So if you were to count the first positive number would be 1. If you were to count, the next number would be 2, 3, 4, 5, and so forth, right? These are your natural numbers, your positive counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Notice no fractions, no negatives, and more specifically, we start at 1, so we're missing 0. Right? So this is the smallest subset. All right, we then move into what we call the whole numbers, right? And the reason why I started here is because the whole numbers are, again, they're the positive. The whole numbers are the natural numbers. They are the positive counting numbers. So everything I just introduced below, 1, 2, 3, 4, 5. Yes, that's a natural number, but it's also a whole number now. All right, so if a number is natural, it's automatically whole. Or sorry, if a number is whole, it's automatically natural. All right, the difference is, so yeah, we have the positive counting numbers, but now we're going to include 0. All right, so the natural numbers start at 1. This set starts at 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah, blah. All right, the easiest way to remember this, right, is it's the natural numbers, 1, 2, 3, but it is called whole, all right? It is called the whole numbers, right? The other word or another way to pronounce that, or same pronunciation, is whole, right? And when we think of a picture of a whole, looks like the letter 0, or sorry, number 0. So there it is. So those are our whole numbers. All right, and the last subset are the integers. So again, if it's real, it's rational or irrational. If it's rational, it could be an integer, whole, natural. It could be a combination of all three of these. It could be an integer, whole, and natural. It could be just an integer and a whole. It could be, right? So you just gotta check. So what an integer is, all right? It's any positive whole number, right? So again, those are just what the whole numbers are. It's any positive it's any positive counting number, including 0. All right. Now notice the only numbers we have not talked about yet. We have our decimals and our fractions. We have 0. We have 1, 2, 3, 4, 5. The only thing we have not classified yet is these include the negatives. All right. So this is -3, -2, -1, 0, 1, 2, 3, yada, yada, yada. Right, these are the nice numbers. And there it is. Those are our numbers. So I like to tie that all together with a diagram, right? So your numbers, right? You got two options, right? You're real or you're imaginary. All right, we're not going to get into the imaginaries yet. Maybe you've learned about them, maybe you haven't. All right, but once you're real, you get broken down. You're either rational or you're, irrational. Those are your options. All right, once you're real or imaginary, you're rational or irrational. If you're rational, right, you can then be an integer, which then could lead you to a whole number, which then could lead you to a natural number. All right, and an easy way to see that is if a number is natural, let me give you an example of that. 2. 2 is a natural number. It is a positive counting number. If it is natural, it is automatically whole, it is automatically an integer, it is automatically rational, and it's automatically real. Right? So once you're at the bottom, you're automatically everything above. Right? So if you get a whole number, if a number is whole, it is automatically everything above. If a number is an integer, it is automatically everything above. Okay? So, moving on. I won't dig into these guys. I will dig into the graphing though. Alright? So, graphing the numbers. Alright, first thing you got to realize, alright, if I don't give you the graph, you need to draw it. Right? So, you would draw your line. Big thing here would be you got to make sure it extends forever on both sides. Another big thing, always mark where your 0 is. All right. Next thing, you need a scale. You need tick marks on this line. All right. What are you going to count by? Well, just look at your numbers, right? These are pretty small numbers. I could just count by 1. All right. So 1, 2, 3. 1, 2, 3. I don't think I'll need anything bigger than that. All right. Now all we do is plot these points on the number line. All right, so this is an easy one, 2.666. So I know I'm going to go over to 1, 2, all right, and it's going to be just below 3. Now, is this exactly 2.6 repeating? No, but I'm going to put a dot where I think it is. I'm going to fill in that hole, all right, and I'm going to label it now 2.6 repeating. All right, now that I labeled it, all right, I can't argue it. All right, I'm telling you that's where 2.6 repeating is. All right, now how do I handle situations like these two? All right, I don't know what the square root of 2 is. Well, if I don't know it, let me get out my calculator. All right, I'm just going to type in the square root of 2 and get that as a decimal. All right, type in the square root of 2. You'll get 1 point something. I don't know what it is. All right, but it's definitely bigger than 1 and less than 2. All right, so if it's bigger than 1 and less than 2, it's going to fall somewhere here. Again, I don't know exactly where, but I'm just going to put a dot in there and say, hey, that's the square root of 2. Last but not least, negative 5 over 2. Again, if you don't know what that is, get a calculator out and you could type in, and you see that's negative 2.5. Now I know exactly where to put that. Negative 1, negative 2. So negative 2.5 is somewhere right here. May not be exact. We put a full circle in there, and we just label it. So once you label it, you're right. Simple as that. Okay, our properties of numbers. We have 9 of them. All right. We have the commutative property, we have the associative property, we have the identity property, and we have the inverse property. All right, these 4 work with both addition and multiplication. So there's the associative of addition. All right, there's the associative of multiplication. So that's 2 different ones right there. All right, they work the same way, but you can see the only difference is addition and multiplication signs. We have the identity of addition, the identity of multiplication, right? So another 2 more, right? The only one that's solo is the distributive property, right? You have a number on the outside of parentheses. We know we can distribute that to the inside, keep the sign there, right? So this becomes A times B plus, right? That addition sign doesn't go anywhere, and we distribute the A to the C as well, so we get A times C, right? Those are our 9 properties, all right? The easiest way to remember it, all right, if you're just looking to try to identify, all right, the word cumulative has a root in it, right? The word commute, right? The word commute, we know that means to move, to travel, right? So what I'm looking for, all right, I'm looking at the equal sign, and I'm looking at the left side and the right side. I am looking to see if anything traveled, meaning, right, A is in the first spot here, B is in the second spot here. So I'm looking at the first and second spot here. If nothing moved, if A is in the first spot, guess where A should be on the right side? It should be in the first spot. It's not. It moved to the second spot. So it commuted. That is why this is the cumulative property. And again, you could play that game with multiplication. All right. Again, we just look at the left side and the right side. All right. A is in the first spot. B is in the second spot. We look to see if anything traveled. Well, if nothing traveled, A should be in the first spot. It is not. All right, moving on to the next property, the associative. All right, the word associative, again, has a root in there. It is associate, right? Think about the word associate, right? Who you associate yourself with, right? That means who you put yourself with, who you group yourself with. And that's exactly what we have with the associative property. So just like the cumulative, right, we look at the left side and the right side. All right, again, we could check. A is in the first spot, B is in the second spot, C is in the third spot. So if it is the cumulative, right, these should not line up. All right, A is in the first. Okay, A is still in the first. Nothing moved there. B is in the second. Okay, B is in the second. C is in the third. Okay, C is in the third. All right. Well, what associate means, well, A and B are being friends on the left. All right, are A and B being friends on the right? No, instead, B is now associating himself with C. right? The friends changed. All right. Now, again, people fall back into seeing parentheses and automatically writing associative. That is not always true. All right. It is an indicator. Right. It means it could be. However, it is not guaranteed. And again, we have the same thing for multiplication. You can see that there. Identity. Right. We know what an identity is. Right. The identity is yourself. Right. You do not change. Well, if I do not want to change, right, again, we have addition and multiplication. If I don't want to change something, if I have the number 1 and I don't want to change it, all right, well, what do I add if I'm doing the addition? What do I add to a number to not change it? Well, I add 0. Any number plus 0 is that number. So if you see something being 0 being added to a number, that's the identity. Multiplication, what number do I multiply to not change it? Well, you multiply by 1. Okay. Inverse. All right, inverse means it undoes something. All right, the inverse undoes something. If you turn on the light, I turn off the light. If you tie your shoe, I untie your shoe. Right, the inverse undoes something. All right, so how do you undo addition? All right, well, you subtract. All right, well, if I am adding by 2, how do I undo that? I would subtract by 2. So you would add or subtract by the same number. Right? If I add 5 and you want to undo that, you would subtract 5. If I subtract 5 and you want to undo that, you would add 5. So you automatically lead to 0. Right? If you are undoing addition, it's going to end up to be 0. Right? Well, how do you undo multiplication? Well, if I times by 5, you would divide by 5. If I multiply by 6, you would divide by 6. If I multiply by 1/2. If I'm cutting something in half, how would you undo that? Well, if I'm cutting in half, you would need to double it. You would multiply by 2. All right? So you are always multiplying by the inverse, or sorry, by the reciprocal. All right? 1 over that number. Right? And you're going to get back to 1. And again, we've already talked about the distributive property. Okay, so quickly looking at this, right? I see multiplication happening, right? Let's see what else is happening. So I have negative 2/3 times negative 3/2, right? So this is a multiplication problem, right? Well, notice what is happening, right? They are coming out to 1. They are undoing each other, right? So I know that this is the inverse property of multiplication. All right, looking down below, all right, I have 3 times 4 times 5 equals 4 times 3 times 5. Now I see parentheses, so immediately I'm thinking, hey, this is probably the associative, but it does not guarantee it. So I'm going to look to the left and I'm going to look to the right. All right, associative means they are grouping 2 different buddies. 3 and 4 are buddies on the first side. 4 and 3 are buddies. Did my buddies change? No, they didn't. This is not the associative. All right, well, what else could it be? Well, 3's in the first spot, 4's in the second spot, 5's in the third spot. All right, well, on the right side, all right, if nothing changed, 3 should be in the first spot. 3 is not. 3 is now in the second spot. 3 moved. 3 moved. So this is the commutative property of, and again, multiplication. Okay, so those were our first 2 learning targets, I believe. I dealing with numbers and their properties. Moving on, we're able to represent math phrases in real-world quantities using models, right? So, or using equations, right? So we're dealing with real-world stuff, right? Which are models, right? So you can represent real-time stuff using math equations, right? This is modeling. I believe this is our last learning target on there. I know we're jumping around a bit, all right? So, to do that, right, we just got to read our phrase and use our brains here, all right? We have the word fewer. We've seen that before. Fewer. What does fewer mean in math? Well, fewer means subtraction. All right, well, what am I subtracting? I'm subtracting clearly a number 7, 7 fewer than a number t and a number t. All right, so I'm subtracting this number 7 and t. So I have two options, 7 minus t or t minus 7. All right, now these are very different things, right? These are very different things, and I can prove that, right? If I put the number 1 in for t, 7 minus 1 is 6. 1 minus 7 is negative 6. Two different things. So read what is happening. 7 fewer than a number t. 7 fewer than a number t. All right, so I am taking 7 away. Right? If I have this number t, we'll say t is 10. Right? If I told you 7 fewer than 10, what is 7 fewer than 10? You would say 3. Right? So which one of these models that? 7 fewer than 10. Which one leads to 3? And that would be our second option. Okay? We could then get even real-world stuff, more real-world stuff that amounts to you. You start with $20 and save $6 each week. What algebraic expression models the total amount you save? Well, which number, right? The first thing you identify is which number is changing, right? Which number is varying, or which number has the ability to change, right? If I start with 20, is that ever changing? No, right? But each week I am gaining $6 more, right? So that is where my variable is. So I need a variable over here, which will say x, which represents a number of weeks. All right, so let's write an expression, right? So I have automatically $20, and I'm going to add $6 each week. There it is. Okay, so another learning target was evaluating absolute value and evaluating expressions. Right, to simplify and evaluate expressions as one, and then the other one was to evaluate absolute value expressions. So I have them both combined right here, right, because they're really the same thing. All right, the only thing we've got to realize is what an absolute value is. So what it means to evaluate, right? Evaluate means just plug in. Simple as that. All right, so it is saying A is -5. That means anywhere you see an A, you plug in a -5. All right, and it says B is 5, so anywhere you see a B, you'll plug in +5. All right, a big thing here to remember is when you plug in, it's really just a general rule. When you plug in a value or a number, you should just put that in parentheses. So it's a good habit. So here I have 7 absolute value A, but instead of A I want -5. Right? Since I plugged it in, it goes in parentheses +4 +3 B, or instead of B I want 5, so in parentheses I'm going to put 5 -8. Now we just follow our order of operations, right? Please excuse my dear Aunt Sally. PEMDAS. P stands for parentheses. Now that's not a great model to follow, right? It's any grouping symbol. Absolute value is a grouping symbol. We have to start there. So I have a -5 plus 4. Right? So I start there and I get -5 plus 4 is a -1 plus 3. And again, you could combine some steps here. Right? You could do your multiplication as well. Right? Now this is the only difference. Absolute value means, well, we take the absolute value. What's the absolute value of -1? That's 1. So now I have 7 times 1 plus +1, right? It's the positive value of that. Right? That's what absolute value does. It gives you the positive value. And we continue with the order of operation. 7 times 1 is 7. 3 times 5 is 15. And I believe they should come out to 14. Again, same thing here, right? For B, you just plug in, right? Everywhere I see an X, I'm plugging in a 1. Everywhere I see a Y, oopsies, just the Y, you don't plug it in for anything else, all right? So that 2 stays there, only the Y changes, so where you see that Y goes 1/2, just like that. Okay, that's evaluating. Right, and again, we have another example of evaluating. Now, simplifying is our other aspect. All right, simplifying is our other aspect. So to simplify, you've heard this term before, we are looking for what we call like terms. What like terms are, they have the same variables, same letters, raised to the same powers, right? So, and we've done this before, right? So I am looking, right, when I'm trying to simplify an expression, I'm trying to see if there are other x squareds out there. Well, here's an x squared, anywhere else? No. Here I have a y to the third z. Are there any more y to the third z's? Yes, here. All right, and here I have a yz. Are there any more yz's? No. So let's combine what we can, right? So in red, right, I can combine 3x squared and 5x squared. That gives me 8x squared. Right? In blue, I have a positive 9y to the third z and a negative 4. Positive 9 and negative 4 is a positive 5y to the third z. And the only thing in green is our plus 2yz. And there it is. Simplifying, very easy. You've done that before. Okay? And again, we have two more simplifying problems. A big thing I just want to hit here is whenever there's a negative outside, or even if there is a number outside, you always need to remember, yes, this is a distributive property that we talked about, but you distribute the sign as well. If this was a negative 2 over here, you would distribute a negative 2. People tend to forget that. So now that gives me a negative 3k minus m plus 2k plus 4, or sorry, minus 4m, not plus. Minus 4m. Or sorry, 8m. Yikes. Alright, and we combined our like terms. That gives us a negative k. That gives us a negative 9m. Okay, next learning target. Alright, when we compare sets of numbers, we have two ways we can compare them. We can compare them with what is called unions and intersections. Alright, they mean two different things. Alright, union, the easy way to remember that, the symbol used for union is a capital, it looks like a capital U. Alright, it's a big U. For intersection, alright, the easiest way I remember that, inter has an N in it. The symbol for intersection looks like a large lowercase m, or an upside down U. Alright, those are the symbols. So, let's handle these each respectively. Alright. So, let's handle the union first. Alright, the union. Right, when I want the union of two sets is when we want the elements that are in either. Another word for either is you want what's in both, or all three of them, right? You want everything for a union, right? So what I mean by that, alright, here's A. A is a set. In A contains the number 1, the number 4, bird, and 9. That's what A contains. And B contains pig, 2, 4, and 9. Alright, so the union, I want the union of A and B, and this again what it looks like. Alright, A, U, big U, B. Alright, it's pretty easy. So I want everything in A. So again, everything in A is 1, 4, bird, 9. And I want everything in B. Well, B has pig. What else does it have? It has 2. So pig, 2, 4, 9. Well, notice I already have the 4 and the 9 from the first set, so I don't need to rewrite them, and that's what I have right here. I do not need to rewrite the duplicates. So the union of A and B contains 1, 4, bird, 9, pig, and 2. Okay? Intersection. Alright, and again, you know what intersect means, right? If you think of an intersection, it's when two things collide, what they have in common. So the intersection, oops, I shouldn't use the word both up here, I guess, right? Because the intersection is when you want the elements that are in both of them, or each, right? You want the same, right? The overlap, right? You want the same. So if I go back up to the example and I see in A, there's 1, 4, bird, 9, and B, there's pig, 2, 4, 9, what's the same in both sets? Well, they both have a 4 and 9. So the intersection of A and B, again, it would be written A intersects B. That would just be the 4 and the 9. Those are the only two things that they have in common. And there it is. That's union and intersection.